Welcome to Multiplanetary INnovation Enterprise, or MINE for short. I'm Cade Nielsen, this year's Enterprise Manager, and I'm joined by some of my teammates to share an overview of 4 of our projects: Diver, Trencher, Lunabotics Astro-Huskies, and LunaRecycle. Each of these teams has dedicated significant time and energy this year to their projects, and we're proud to showcase the results of our hard work. Our enterprise is focused on designing, testing, and deploying robotic systems built to perform tasks in extreme environments, ranging from submerged copper mines of the Keweenaw Peninsula to the unforgiving terrain of the lunar surface, with plans to expand further. MINE is made up of more than 80 students from a wide range of majors and interests working together across our 4 main projects.
Hello, my name is Ansel Hartman, and I am a member of the mechanical team on the Diver project. Diver stands for Deep Investigation Vehicle for Energy Resources, which focuses on making a remotely operated vehicle, or ROV, to explore and map flooded mines using LiDAR, specifically exploring local copper mines such as Quincy Mine. We aim to collect data for the possible implementation of renewable energy resources, specifically converting the old mines to pumped hydro storage facilities. This past year, our project has focused on Phase 0, which involves working on a prototype ROV to operate in a pool environment. This initial phase exists to test various sensors on the ROV and its maneuverability, with 1 pool test completed so far this semester.
Yeah, because it like sinks. Just brings its own tether back. That's awesome. You know what's funny is my whole front.
Future stages of the project are Phase 1, which has the goal of reaching a 400-meter depth in the mine, before moving on to Phase 2, where we will reach a 2,000-meter depth, with a full map of the mine.
Hello, my name is Andrew Westfall, and I'm a member of the Lunar Trencher Electrical and Data Acquisition Team. MINE Lunar Trencher is a research-based project with the goal of raising NASA's bucket ladder technology readiness level to a 5 through test validation and demonstration in simulated lunar environments. On this project, our team designs, builds, and tests bucket ladder excavators in simulated lunar conditions and atmospheric. Last year, we concluded our dusty thermal vacuum chamber test campaign and are now working to demonstrate the effectiveness of a chain-style bucket ladder in creating a substantial trench. This is done through mounting our bucket ladder, Lunar Ladder, and NASA's Moonraker on the PSTDL Labs rover hoplite. The key metrics tracked for our project include overall mass, excavation rate, surface roughness measurements, mass deltas, and power consumption over time to compare these between our previous and current test campaigns. This semester, we have finished our detailed design phase and are preparing to enter the build phase in fall semester.
Hi, my name is Audrey Kansas, and I'm part of the Systems Engineering and Integration Subteam for Lunabotics. The Lunabotics project is focused on following the systems engineering process to design and construct a rover to compete in NASA's annual Lunabotics competition, which NASA uses to collect data from dozens of collegiate teams on the design and operation of rovers in a simulated lunar environment. This year, the competition's goal is to autonomously excavate lunar regolith simulant and use it to construct a berm, which on the moon would be useful for shielding lunar infrastructure from debris. Our design this year consists of a single chain-driven bucket ladder for excavation, a single belt for storing and depositing regolith, and 4 independently driven and steered wheels for mobility. The team is currently in the final stages of testing and verifying the rover's functionality before we travel to Kennedy Space Center to compete in the competition this May.
My name is Mason Krause, and I am the team manager for the LunaRecycle Challenge team. The primary goal of the challenge is to transform packaging, structural, and other waste items into anything from tools to structures, because waste isn't always trash. In short, our goal is to turn the disposable into the indispensable. Our team selected Zotec F30 foam as our target waste type. Zotec F30 is frequently used in aerospace applications as a packaging material due to its thermal and shock-absorbing properties. Our system is designed to process this foam through densification, pulverization, and extrusion to reduce its volume and create a viable 3D printer filament. Another consideration of our design was air filtration. As Zotec F30 is heated, it releases trace amounts of hydrofluoride gas, which over time can become an inhalation hazard. To remedy this, a caustic scrubbing unit was designed to neutralize any unwanted byproducts.
The Multiplanetary INnovation Enterprise offers students from many majors the chance to gain practical, real-world experience through active participation in the engineering process. Within our 4 main projects, team members have the opportunity to contribute to mechanical and electrical design, manufacturing, programming, testing, and much more. Our hands-on approach ensures that each member gains valuable experience from the ideation and initial design phase all the way through to the manufacturing and testing of the project. I'd like to extend a special thanks to our members, our faculty advisor, Dr. Paul Van Susante, and our sponsors for their dedication and support in helping us make significant progress this past year. On behalf of the Multiplanetary INnovation Enterprise, thank you for your time.